Internal resistance. By the end of this lesson, you should be able to explain internal resistance, determine EMF and internal resistance, solve problems involving EMF and internal resistance. A boy is playing with a battery-operated remote control car. After playing with it for some time, he discovered that the dry cells in the battery compartment became hot. Why did the dry cells become hot? What caused this heat? As electrons flow through the light bulb, the wire becomes hot. The atoms in the bulb filament and nichrome wire become more energetic and vibrate with greater amplitude. The paths of the electrons in motion are hindered by the vibrating atoms, and thus the electrons flow at a slower rate. This hindrance to the flow of electrons is known as resistance. As a result, when the temperature of the conductor increases, the resistance of the conductor also increases. Resistance in a conductor converts the electrical energy supplied by the source into heat. Hence, when current flows through the dry cells, they become hot due to the internal resistance in the dry cells. The internal resistance R is the resistance within a cell or source of electricity. What causes the internal resistance within a cell or source of electricity? A standard dry cell battery is made up of a zinc case, a carbon rod, electrolyte, ammonium chloride jelly. Chemical reactions within the battery cause electrons to be stripped away from the carbon rod electrode. These electrons will flow through the electrolyte to be collected on the zinc case, which acts as the negative terminal. The carbon rod consists of atoms with shortage of electrons and therefore act as the positive terminal. Electrons will flow from the negative terminal of the battery to the positive terminal through a wire in a complete circuit. The force to move electrons around a circuit is called the electromotive force and is measured in volts. The rate of flow and production of electrons within the battery depends on the material that made up the electrode and the electrolyte. Electrolyte or chemical material opposes the flow of electrons in a battery. Hence, a battery has internal resistance. A car battery, which is also known as lead-acid accumulator, has a smaller internal resistance than the dry cell. The electrodes of the car battery are made up of metals with large surface area and placed in the electrolyte. The following table shows the EMF and the internal resistance in various sources of electricity. A real battery can be thought of as a source of EMF, E, with an internal resistance, R, all connected in series. The internal resistance R is included in order to determine the power lost. When current flows through the cell, a voltage develops across the internal resistance. This voltage is called the potential difference due to internal resistance VR. What is the potential difference VR across the internal resistance R when current I is flowing through it. From Ohm's law, the potential difference VR across the internal resistance equals to current I times the internal resistance R. What is the potential difference across the external resistance R when current I is flowing in the circuit shown? From Ohm's law, the potential difference across the external resistance equals to current times the external resistance R. The potential difference across the terminals of the cell is denoted as V. In a closed circuit, potential difference across a cell V equals potential difference across the external resistance VR. Potential difference is a measure of energy per unit charge. Hence, the EMF of a cell equals to the sum of the potential difference across the cells in a closed circuit and the potential difference across the internal resistance. Since the potential difference across the cells in a closed circuit equals to the potential difference across the external resistance, the EMF E can be rewritten as current times the external resistance plus current times the internal resistance, or current times the sum of the external and internal resistance. What is the EMF of the cell? The EMF of the cell is 1.5 volts. What is the potential difference across the cell and the electric current when the circuit is closed? The potential difference across the cell is 1.2 volts when the current flow is 0.3 amperes. What is the potential difference lost due to internal resistance? The potential difference lost due to internal resistance is 0.3 volts. What is the internal resistance of the cell? The internal resistance of the cell R is equal to the potential difference lost due to the internal resistance divided by the current. Thus, internal resistance equals to 1 ohm. What is the resistance of the light bulb shown in the circuit? Using the equation, the potential difference across the cell in a closed circuit equals to the potential difference across the external resistance, and the potential difference across the external resistance equals to the current times the external resistance. Hence, the resistance of the light bulb is 4.0 ohms. Two identical cells are arranged in series and in parallel in the circuits shown. Each cell has an EMF of 1.5 volts and an internal resistance of 0.5 ohms. What is the effective EMF for two cells in series? The effective EMF of cells arranged in series is equal to the sum of the separate EMFs. Hence, the effective EMF for two cells in series equals 2 times 1.5 volts equals 3.0 volts. What is the effective internal resistance for two cells arranged in series? The effective internal resistance of cells arranged in series is equal to the sum of the separate internal resistance of the cells. Hence, the effective internal resistance RE equals 2 times 0.5 ohms equals 1.0 ohms. What is the effective EMF for two identical cells arranged in parallel? The effective EMF of cells arranged in parallel is equal to that of one cell. Hence, the effective EMF for two cells in parallel equals 1.5 volts. What is the effective internal resistance for two cells arranged in parallel? The effective internal resistance of the two identical cells arranged in parallel is given by R over N, where N is the number of cells. The effective internal resistance RE equals R over 2 equals 0.25 ohms. In order to find the EMF and the internal resistance of a cell, the circuit is set up as shown. The EMF, E, and the internal resistance R can be derived from the graph of potential difference across the cells, V against current I. From the graph, what happens to the potential difference across the cells V when current I increases? The potential difference across the cells V decreases as current I increases. Potential difference across the cells V decreases linearly with current I. From the formula, EMF E equals V plus IR. The potential difference across the cells V equals negative RI plus E, where V equals vertical axis, I equals horizontal axis, negative R equals gradient of the graph, E equals vertical intercept. The equation for a straight line graph is given by y equals mx plus c, where y equals vertical axis, X equals horizontal axis, M equals gradient of the graph, C equals vertical intercept. Comparing equations 1 and 2, 1. V equals negative Ri plus E. 2. Y equals mx plus c. V and y are the vertical axis. I and x are the horizontal axis. E and c are the vertical axis intercepts. And negative R and M are the gradients of the graphs. From the graph V against I, how do you determine the EMF E of the cell? What is the EMF E of the cell? The EMF E equals intercept on the V axis. E equals 3.0 volts. The EMF E of the battery can be obtained from the intercept on the voltage axis. The value of E to be 3.0 volts. From the graph V against I, how do you determine the internal resistance R? The internal resistance R can be determined from the negative gradient of the graph V against I.